Welcome to part 11 of Zombies and Reinforcement Learning. Today we are going to build the model. So let's go ahead and we are going to create a model.py. And the first thing we're going to do in our model.py is get a few of our imports in. So we're going to import torch. We're going to import torch.nn as nn, and we're going to import torch.nn.functional as f. All right, and let's talk a little bit about our structure here. So we're going to create a zombie net. It's going to have 4 CNN layers, so 4 convolutional neural networks, because the observations in this case are image observations. Obviously, if you had some other numerical observation type, you might not need that. So we're going to have 4 CNNs, and then we are going to have 3 FC layers, fully connected layers. So 3 of sort of your standard linear layers. And then our output is going to be, let's see, what did I make the output? All right, our output is going to be action dimensions. So output equals action dim. All right, and what that's going to end up being is something that looks like this. All right, so it'll output something to this effect, and then we'll basically pull this out and say, hey, this was a 2, or an action 2. All right, let's go ahead and get started. So we're going to say class zombienet inheriting from nn.module, and we're going to go ahead and define our init method. So def init, and that auto completed more than I wanted it to. So we're going to take in action dims. Hidden dim is going to be, I believe we're going to end up with 1024. So let's go ahead and make that our default. Also, that doesn't need to be a plus. Okay. We'll default dropout to 0. And observation shape will be none. Okay. Here we're going to call super with self, and actually zombienet and self, and self. Okay. So let's go ahead and define our convolutional neural networks here. Self.conv1 is equal to nn.conv2d, and we're going to say in channels will be 1, out channels will be 2, or sorry, out channels will be 8. Kernel size is 4, and stride is 2. And I kind of mentioned it in the last video. I'm going through this section with the assumption that you kind of already know how to work with neural networks. If that's not the case, you should definitely go and take a course on convolutional nets. and neural networks in general, I can put some recommendations down in the video descriptions. There's some great stuff out there, but this is not intended to be that. This series is focused on the environment creation and environment conversion. So I'm not going to try to go into depth here, and there are better people to cover it anyway. All right, we're just going to copy that a few times. So this is going to become conv2 and 3 and 4. Okay. And then instead of in channels 1 here, we're going to say 8. So you always want to line up your in channels of the next network with your out channels of the previous network, because these are going to flow in, and you generally kind of stair step them up. So what a convolutional net is doing effectively is it's going to take, your image data, it's going to slowly collapse that down into actual data among X number of channels. It's going to try to extract features from the image. And if you're wondering how I picked this particular number of layers, and a lot of it was experimentation. This is what ended up working for the problem. Okay, and we're going to make, as we get smaller, we're going to make our kernel size smaller, and we're going to keep stride as 2. All right, and then in channels here is going to be 32, and out channels is going to be 64. And our kernel size, again, will be 3. Okay. We're going to implement pooling. Is equal to n.max pool 2D. Okay. Kernel size equals 2. And stride equals 2. Okay. I decided instead of, and this is just useful if you end up playing with various channel sizes and numbers, we're going to define a function to calculate the convolutional output. So let's go ahead and do def, and we'll come back up to the init method in a minute. We're not done. Calculate conv, I did that plus again, conv output, and self and observation shape. Okay. And we're going to say x equals torch dot zeros, and we'll say 1, and star observation shape. And then we'll do x, and this will mimic what we're doing in the forward pass, equals self.pool, f.relu, self.conv1, x. Okay. And then we will do x equals self.relu, self.conv2, x. And then really this next one will look a lot like the one up above it, except this will be conv3. And we're going to copy that one. Z. And this will become conv4. Okay. And then finally, we're going to say return x.view. This will reshape it. -1 dot shape at 0. All right. So let me just look at this and make sure I got it right. Yep. Torch.zeros, conv1, conv2, conv. Oh, I did self.relu, and that should be f.relu. There is no self.relu. All right. That now looks correct. Conv2, conv3, conv4. So what this is going to do is this is going to calculate the output size coming out of this. So it's not 64, it's not a number that we've set. It's based on the size of the image coming in and the size of the image coming out after processing. So this is not, and there is a way to figure it out mathematically. Personally, I find just having a function in here that runs it through once and determines the size to be a lot easier for me. So I'm going to go ahead and say back in the init method, we're going to say conv output size equals self.calculate conv output, and we're going to feed in observation underscore shape. Okay. And then let's go ahead and print it out. This is a good output size. Okay. This will only happen once in the init method, so it's not like it's going to spam your output. All right. Now we can go ahead and set up our, let's add some comments and make this a little cleaner. Okay. Okay, so we've got our convolutional layers and our fully connected layers. Let's go ahead and say self.fc1 equals nn.linear. And this is going to be conv output size, hidden dim. And normally this would be a number, some thousand something random number coming out of this process. Not random, but you know what I mean. So, and we just get to plug in a variable. Self.fc2 equals nn.linear. And this is going to be hidden dim, hidden dim. We're going to copy and paste that one. And self.fc3 will become just the exact same thing as fc2. And then we're going to do self.output. And let me see if I'm even using fc3. I am using fc3. All right. Wanted to make sure we weren't adding that needlessly. All right, self.output will be nn.linear. And that will be your hidden dim and your action dim. And I realize up here I put dims. Let's just clean that up and make it dim to match the tense of the rest of these. All right. And then we will do self.dropout equals dropout. That's just going to be a value. And self.apply, and we'll be defining this in a moment, self.weights init. All right, let's go define our weights init as soon as I find it. All right, let's just go ahead and put it right under here. So we're going to define weights init, and what this helps us do. So out of the box, you're going to get a bunch of random weights in a network. When you create just a blank neural net, random weights, initializing the weights a little bit more purposefully can help make sure that you don't have any weird outliers in the beginning that throw training off. So not always important. In this case, it did help stabilize things a little bit and help training. So we're going to say is instance m of nn.conv2d. Okay. So if it's a convolutional network, we want to use nn.init.timing normal on m.weight. And we want to define our nonlinearity as ReLU. And then if m.bias is not none, then we want to say nn.init.constant and m.bias and 0. Okay. Now we're going to fall back here and do elif. Nope, over too far. Okay. So elif, we'll do is instance, just like we did before. M of nn.linear. Okay. And I see it's erroring because I did elify. That is not what I intended there. Then nn.init.xavier, we're not going to do uniform, we're going to do normal. Make sure you get that underscore at the end. M of nn.linear. Okay. Let's see. And I should not have put that colon there. Okay. If m.bias is not none, then we're going to do nn.init.constant m.bias 0. Okay. So this function should basically get all of the weights to Kyming normal for conv2d and Xavier normal for all of the linear layers. Okay. So finally, let's go ahead and start to add our forward method, the meat of this model actually doing something. So we're going to say def forward. And it's going to take self and x as parameters. And then this is where, so if you remember back in when we were setting up the game, I mentioned that we would need to store, normalized values. So values between 0 and 1 for images, but that we couldn't store them right off the bat because we were going to need to, because that would make a giant input buffer. So our observation is returning something that's going to have, numbers between 1 and 255 in it. So now over here in the model, the first step of our forward method needs to be x equals x divided by 255. So we're just going to go ahead and normalize those images on the first layer. Now we can do, really, we can come up here because this is going to be very similar. So we can copy and paste. And we don't need this one, so we can get rid of that. But everything else basically can stay. That's all right. And then we can do our x equals x.view, x.size 0, and -1. Okay, and then we can do our fully connected layers. So we're going to do x equals f.value, and we'll do self.fc1 and x. And then we're going to actually make a dropout optional. So we're going to say if self.dropout is greater than 0, then we want to go ahead and call x equals f.dropout. So we're using torch functional. xp equals self.dropout. That's dropout percentage. Okay. And then I'm going to go ahead and okay, that didn't get quite what I wanted. All right, so we're just going to go ahead and copy that. And I am going to come down here and we're going to put another in between. We're going to go ahead and do x equals f.value. And this is going to be self.fc2 of x. Okay. And then finally down here, we are going to have x equals f.value, self.fc3 x. And then we'll do output equals self.output x. And you don't usually want dropout between your final layer and your output layer. That tends to make performance worse. And we want to return output. Okay. Now we need just some helper functions here, both inside and outside the model, or outside the class. So we're going to define save the model, and we're going to say self, and we're going to say file name. We'll be feeding in one later, but we want to go ahead and give it a default. So this will be models/latest.pt. Okay. So we're going to do a try. Actually, no. For saved model, we're not going to do our try. We're going to do a try on load. So for save the model, we're going to do torch.save and self.stateDict and file name. Okay, and then we'll also do def load model. And for load the model, we'll take the same params. We're going to say self and file name equals models/latest.pt. Okay, and then here we'll do a try for self.loadStateDict torch dot load file name, and print. So if this worked, we're going to go ahead and say printf loaded weights from file name. Okay. And accept. And the only thing we're going to catch here is a file not found error. So we're going to say accept file not found error. We kind of want anything else to just go ahead and crash. We're going to say print f no weights file found at file name. Okay, so there's our load the model successfully. And then we're going to define two other functions that are outside of the model itself. And we could stick these anywhere, but this is just the most logical place for me to put them. So we're going to say def soft update target source and a tau. So in DQN, we're actually going to have two value networks, and then each value network will have a target network. And that target network is intended to lag behind the primary network, and it provides a certain degree of stability by lagging behind. So the soft update and hard update functions, soft update is basically intended to allow us to soft update that target and keep it close to the main network without quite having the same swings as the main network. So we're going to say tau equals 0.005. That's our update amount. And then we're going to say for target param. Now, if I could type param in zip target.parameters. Oh, I misspelled target as well. Okay. Okay, so for target.parameters and source.parameters. And we're going to do target param .data.copy. And it's not autofilling here because it doesn't know what these params are. Target param .data times, let's see, and we're going to do 1.0 minus tau. So basically what we're doing, well here, let me finish typing it and then I'll explain it a little bit better. So plus param.data times tau. All right, so let's think about what's happening here. So in our soft update, we are basically saying you've got a target param and a param, so the source model. So in the target model, we're saying that we're going to multiply the target param by 1.0 minus tau. So tau is very, very small. So this is going to be, let's say our target param. So let's say target is 5, and they wouldn't really be nice round numbers like this, but let's assume they are. So, and then let's say that source equals, we'll do 7. We'll say source is 7. So let's go ahead and pull up our calculator. And we're going to say that, so target param, so 1.0 minus 0.005 is really close to 1. So we're going to multiply that by our target, which is 5. All right, so what we end up with is a number that's super close to 5. So that is 4.975 would be the value of the left side here. And then our 7, our source, which is what's coming from param.data, times tau, 0.005, so our very small number. So that ends up being 0.35. And if we add that, so 0.035 to 4.975, we end up with 5.01. So what's the point here? What are we doing? So what this does is it very, very, very incrementally edges the target towards the source. So in this case, our target was 5, our source was 7, and it is incrementally moving 5 towards 7 by 0.01 in this case, based on the value of tau. Obviously, if tau was larger, then we would move towards that value more quickly. We actually don't want it to. We want it to intentionally lag behind a little bit. So, all right. We can get rid of that. That was just for demonstration purposes. We are also going to do a hard update. So just copy that, paste it, and then we're going to change the word soft to hard. And we no longer need tau because this is just going to be a direct copy. And in this case, instead of copying this whole thing, we just need that. All right. Now the last thing we're going to do before we exit the video here is we're going to go ahead and test and just make sure that our model actually returns something, or at least can be created. I think can be created is our target here. So let me go and take a look at our agent code. We're going to go ahead and create an agent.py. And we won't be using very much in here right now. I just want to go ahead and from model, import ZombieNet hard update, soft update. And we're going to go ahead and say model, we'll delete this part later, but I just want to go ahead and test it. So model equals ZombieNet. And we will say that action dim is 1, and hidden dim is 1, and hidden layer, let's see, dropout is 0.1, and observation shape is 4. I'm making all of these numbers up. I just want to make sure that it actually creates and doesn't give us any errors. And we're just going to run agent.py, and it says cannot import hard update from model. Okay. Let's go see what we messed up. It may just be that I didn't save the file. All right, I'm going to resave and rerun. All right, must be an iterable, not an int. Okay, that's fine. It's expecting something like this, I believe. We'll play with this for a minute until we get it right. Nope. Let's see. Do you need a list? Yeah, I think it does. I think it needs... Okay. So it didn't like input size 1, 4. Expected unbatched. Let's see. I think right now what we're dealing with is just that my test data here is not really mimicking the live data very well. Hang on, let me play with this for a moment. All right, so I found the issue. We needed to pass in parentheses 12828. That is going to mimic the batch size and then the image size that we're passing in. And we are getting an error. So let's go take a look and see what that error is. This is why we test. So let's see, model, yep, fan out. So it's saying linear object has no attribute dim. And that is happening on line 43 in weights init. So let's go take a look at 43. So Xavier normal mm of nn dot linear. And let me take a look at my working code. And we'll see what's going on here. Okay, so it seems like it's not liking, okay, elif is instance, nn.init.xaviernormal. I see what's going on. It just wanted m.weight here. That was my fault. Okay. Okay, let's save and go run it again. All right, and you'll notice that we got our convolutional output size of 64. And the cool thing about doing this dynamically is it means you can play with various variables and see what they would do to your output size. So like if I come in here, and obviously you can do that anyway, it just takes more math to do it without. So if I come in here and I make this 32 and rerun it, now we have an output size of 32 instead of 64. Not normally quite the linear mapping that we just saw there, but you get the idea. All right, so at this point we have our model. It's working, at least to the point of being able to create it and not throw errors. And that seems like a good place to end the video. In the next video, we're going to go ahead and build out this agent class so that we can start to move towards training our model. So I will see you in the next video.